Mm, I'll try to stay here so I can actually capture my voice. I added a few things to this week's module. So I posted a possible solution for homework 4. Okay, there are different way of doing it. A possible solution. So make sure this is the actual code that you run. This is a function. So you have to take that function homework 4 out. So it will be able to run. Put them in the same folder. So some of you talked to me and some of the student had trouble rearranging the equations and then using ODE for the second part. So this is actually the answer to the second part. I'm sure everyone did good on question 1. So take a look and see how it was done. But if you go back to the lecture, you'll see when we talk forward dynamic and inverse dynamic, we're using forward dynamic. We're putting theta double dot on one side, everything else on the other side, because we want to find the acceleration. We had some initial condition, right? And then that's the way to do that. And it doesn't matter how many mass system you have, you just organize your equation that way and ODE will take care of it. You just have more output coming out of ODE, all right? So it will give you the position and velocity of each link, and they are independent. They are dependent. So some of you try to drive the equation independently so you will solve it. It's not possible, or it's very, it's a long solution if you wanted to go that route, all right? Yeah, some of us experienced that. I also put the possible solution for CP23. There's also a file for error propagation. That's what we're going to talk today, but I'm not going to go into detail of how the model was developed. This is a good source for you to, if you're interested in wheeled robot, this is a good source to study and you'll understand the equation that we're using today. Sounds good? All right. Let me stop this so we can share from the iPad and I can start the lecture. I think everything is graded except homework 4 and fall foliage. I started grading, I'll finish that today or tomorrow. And homework 4, I think will be after Thanksgiving, right? Depending on how you feel.
Yeah, it looks like it's 5.
Yeah, because Brett is grading them mainly, and I will just take a look at the videos if someone had animation. Otherwise, Brett will grade. All right. So for today, I chose wheeled robot dynamic is independent of what we had so far, and I think this was a good opportunity to fill this in. So if you remember from our very early discussions about degree of freedom, we said that if a robot, like it's a mobile robot and it's not moving in Z direction, right? So ignore the suspension that has a minimal Z elevation change. If we think about the direction, you're only going X and Y and turn also, so it has a theta. So we can give it 3 degrees of freedom, right, on a planar. Especially the 3 degree of freedom is when we are dealing with differential drive robots. Let me fix this. When we are dealing with differential drive robots or DDR, because right and left wheel will spin separately. So you can control the heading, you can control theta. So that's why we have 3 degree of freedom. X and Y, and you're also controlling theta, it's independent, right? So if you're going to write, to come up with the equation, if you are going to write kinematics and dynamics of this, you should be able to do it. That's why we don't teach wheeled robot generally in this course, because as long as you know how kinematic and dynamic works, you should be able to do this on your own. So, but what we're going to do at the beginning is to develop kinematic and dynamic for this. And then to design a controller, you just usually we're using PID controller for DDRs because they use DC motor. They're basically controlling the DC motors, right? That will that basically you're controlling the wheel velocity, and that's how the car will move. So the whole problem should be accessible for you because you have the knowledge. So you have the knowledge of developing and controlling this. Now, if we assume P, the position, okay, of the car at any point, we have three states in it: X, Y, which we're controlling, plus theta, which is the heading, right? Usually see heading on P, but here we're using theta. And you see that if you draw a vector, velocity vector here, if this is the velocity of the car, from the center of the mass, perpendicular to the chassis of the car, if that's your velocity vector, the angle that builds with the frame of the robot, that will be your theta, right? So when you rotate, you can calculate that. Now, frame of the robot at the beginning will be in the same direction of this, I'm gonna say B, the frame of the board frame. So if the bigger XL or XI and YI, that's actually Y. If that's your board or your fixed reference frame, let's say, you could have a reference frame on your car, right? So when you rotate in the car, the reference frame on the car also rotates. So if I go here, now my reference frame on the car will be in this direction. You see that it's changing with respect to this board. So if you have the rotation matrix between the two, which depends on theta, right? What direction, what is the rotation for the car? What kind of rotation this car has? It has a pure rotation, right? Let's say we want to find the rotation, the relationship, the rotation matrix between the board and the car reference frame. From the way, the motion that you see, do we know what kind of rotation it is? So where's the Z axis of the car? Rotation on Z axis. The board and the car Z axis are in the same direction, right? So all you have to know what is theta. And you have theta, that is how you use that to create your rotation matrix about Z axis, which is like 1, 0, 0, 0 cosine theta, sine theta, 0, negative sine theta, cosine theta. So at any time that you have that theta measured, then you can know where the car is with respect to the board. So if you find the velocity of the car with respect to its own frame, then you can easily find the velocity of the car with respect to the board, reference frame, or observer that is fixed in place, right? So we should be able to do that from what we learn in kinematics. Now, if the position is x, y, theta, what's the velocity? We are trying to find the kinematics. So P dot would be x dot, y dot, theta dot, right? So I can write x dot is cosine theta v, y dot is sine theta v, and theta dot is omega. Now let's see what they are. This v is your linear velocity, and this is your angular velocity, well, of the car, right? So if you had the velocity vector and you had theta, you would know what x dot is, what y dot is, and theta dot is just omega is just theta dot, right? The angular velocity. So now in differential cars, DDRs, we said that we can control the right and left wheel velocity, right? So I can say that if this was the linear velocity of the right and left wheel, I can say, let me redraw that. It's cleaner. I redraw here. This is the wheel. This is the center of mass. Pardon my drawing. So if we say this is B, this is B. So if that's the axle, so each wheel is B from the center of the car. And if the radius of this wheel on both sides is r, I can say then the linear velocity here going to be r phi dot L, right, left, and r phi dot r. So this is left wheel, this is right wheel. All right, now, maybe we can move this guy here. All right, that's probably better. Now, if I want to write an expression to relate these two together, I can say v plus b omega is r phi dot right wheel, and v minus b omega is r phi dot left wheel. Now, in differential cars, how in what scenario we will move forward? Well, we move on a straight line because we can turn right, left, turn in place, and we can go straight, right? In what scenario we will go straight in differential car? So both of the velocity are the same, they're rotating in the same direction, right? So that will give us a straight line. So if you want to control on a straight line, you have, so your variable here, what you have is the velocity of the wheel itself. How do we get those velocities? There's a DC motor, right? So if we have a velocity of the DC motor, then we can come up with the velocity of each wheel, and then this is the relationship to get the relation between the velocity of the car and the linear and angular velocity of the car. Now, if we wanted to turn right or left, what would we do? So one of the wheel has to rotate, right, in the opposite direction of the other one. Now, if both of your velocity in opposite direction are equal, what's going to happen? Rotate in place, right? To turn right or left, what should happen? One of the velocities should be less than the other one, right? So the path that that wheel will take with a higher velocity is longer at the same time. So that's how the turn happens. So basically controlling the motion of a wheeled robot comes down to the value and the direction of the wheel velocity, right? Agreed? Okay, now let's write the dynamic for this. So when we have DC motor for our car, for the wheels, we definitely have torques, right, for each motor. So torque is not going to be zero here. We're going to have torque. So I'm going to call this tau left and tau right, TL and TR, and see if you can write TR wheel torque. Or do you think you can start writing and developing the dynamic for this? Try, and then I'll write the equations. Just want to know if you can play with it a little bit. I definitely need another page here. Nope, go back. Say, I'm gonna say I. So you can use the kinematics that we learned. Yes. Yes, I can. Which one did I do last time? So basically you can use kinetics, sorry, not kinematics. Kinetics to develop the same thing that we did for our manipulators. We're doing the same thing here. So here we have inertia, we have thing called inertia. That's not that, that's oh my god. And so we are here using the moment actually. Not using kinetic, just using Newton's law, but you could use kinetic energy and then develop all of that. And then if you calculate V dot omega dot, these are useful if you are using mobile robot control robotics. You can always use these equations. That's why I brought it here. Tau R, tau L. Now, if you put them together, tau R, tau L is going to be 1 over MR, MR, P over IR, P over IR inverse. You're just substituting. And then P double dot R shows up. Now, basically, we're gonna get a mass matrix. So if you use kinetic, you would arrive to mass matrix directly. 1, 2, D21, D22 times P double dot R. So this is the wheel velocity. And here, D11 is equal to D22 R square 4M plus R square 4B square. And your D12 is D21. That's what we expect because mass matrix is symmetric. R square 4M minus R square 4B square. Hopefully I wrote the equation correctly. I will check again. Yes, that's negative, that's positive. Right, this is correct. Now, this is if we don't have any damping. Now, if you have damping, you have the suspension and you want to bring those in. So if we include damping terms, then we get negative B dot, which is, so B is our matrix, B R right wheel theta dot R, and then minus B2 of the left wheel theta dot L. I can actually write here L. So, and then what your dynamics become? So you have D phi double dot plus B phi dot equal to tau. So, and we know that tau here is tau L and tau R. So you see that we ended up getting the same general dynamic equations, right? First of all, we know how to solve this. We have done it before. So this is gonna be one mass system, just have the car. So it will be basically question 1 of problem of homework 4. But the difference of tau is not 0. You're gonna have value for tau, which is the torque. Now, if you wanna control this, usually we use PID controller for DDRs because of the DC motor. And what are we controlling here if we develop a PID controller? So the variable here is the velocity of each wheel, right? We control that through controlling the DC motor, right? So when you're writing controller, you go back to where we had the DC motor block diagrams, all of those, right? So right wheel, left wheel, and then you can control the system. Really from here, you have already done it. So usually coming to the equation and you see that usually become a second order system and you should be able to do it for any system, right? So your job is to developing that. So usually we use a low level PID controller. And which allow to control, so to control motor, position, and speed. This is important to allow wheel speed and position. Position, that's the kicker here. I'm gonna write with Ray. Assuming no wheel slipping. Yes. So D here, this is the D matrix that I developed. I don't want to write the whole thing. B is here, comes from this. So if you write that in a matrix form, so your theta dot is theta dot L, or theta dot L. So this is your B matrix. You just have to write this in matrix form, which is negative BR, 0, 0, negative BL. So that is your B matrix. Why are we doing that? Because we want to put that in the second order differential form, and from there we know what to do. We have done it before. You can literally use the same controller you developed and apply to this. You can solve the dynamic using OD45, right? So your control object here will be, what will be your control object? What would you want to do if you had a car, robotic car, let's say this? What would be your objective here? We need to know what the problem is, right, to solve it. Okay, so I can do this. You're right. I need to go from point A. Well, I'm going to put point A here because this is confusing even for me. So point A, right? I want to go to point B, correct? So I want to make sure I get there. What else is important? Can I do this? Like, I might, right? So the heading control is also important. How am I getting there? Am I supposed to go on a straight line, or I have, so if you have obstacles, then you have to go around them. That's a different case, right? But if you were going straight, your problem was go straight and then turn and then go back there, right? So you didn't have obstacle, then your objective will change. That's what you have to control. Now to go on a straight line, we just said what should happen to the two wheel? Same velocity in the same direction. It will go on a straight line, hopefully, right? And then when you're turning, if you know the radius, you're gonna adjust the wheel velocity and then go straight again, correct? So now this is, so for odometry here, usually the DC motors come with encoders, so they can tell you what's the position, what's the velocity, right? So that's from the encoder. First of all, there might be some error in the reading, right? What else can go wrong? Because usually, do you expect that just go on a straight line, go on a straight line? You probably say, I was gonna go on a straight line. This is the velocity, but this happened. I ended up getting where I wanted, but I wiggled a little bit on the way, right? What could cause? One was the resolution of the encoder on your DC motor. What else can happen that the car will deviate? Yeah, so if there is like a structural, right, error, it will impact, right? Because the two are not then in the same direction. What else? Andrew? You don't know? You drive a car? Have you, don't do it, especially when you're going fast. When you're going fast, have you had your wheel, like hand off from wheel, see how long you can go on a straight line before you turn it? No? It's fine, don't do it. But to see like, so if you don't go on a straight line and then your car starts turning, what's wrong? Huh? Your alignment, you have to go see your mechanic, right? Your steering. So now imagine I'm doing that and my car pretty good. Go, you're on a straight line and hit a bump. So definitely I have to grab that back, right? So the environment also will impact. So the misalignment of the axial, the steering, right, system, and also the impact of the environment. So if the floor, if the road is not paved or is not flat, and you have some debris, depending on your wheel size, the debris will impact or not. But if you're going over a speed bump, definitely going to impact, right? So we said that this is correct. You can use that equation. If there is no slipping, there's no error, everything is good. What if there's not, right? What if we have all of this? We have two kinds of error, deterministic, non-deterministic. For deterministic error, we can calibrate and see it to happen. So we can compensate. We can bring it in our controller. And there are non-deterministic, we cannot do anything about it, right? So in this lecture, we're gonna check, okay, what if we could model our error that happens and then bring that to our calculation. So when you're designing your controller, your compensator, you compensate for all of those errors that might happen. So your real robot will go on a straight line. Now think about, you can have a robotic arm attached to this real robot that goes from one point to another and pick object. If you remember one of your homeworks at the very beginning about transformation matrices, it was a mobile robot with an arm. Now you have both of those knowledge. You attach, and then from here you should be able to model this whole system, right? I'm not expecting you to do it right now, but I'm just saying you have the knowledge to do that. This will hopefully will be the last piece of the puzzle, how to account for those kind of errors. All right. Yeah, let the fun stuff begin. Now, to model for odometric position, we're going to look at it as, okay, what is the error that can happen? So we are in X, Y, and theta direction. We have 3 degrees of freedom, right? We might have some error in X direction, some in Y, some in theta, delta X, delta Y, delta theta that are not desirable. But we are counting it as if, okay, if we had those X, Y, theta position, plus some extra distance or angle in that direction. So that's going to be our function. You're going to look at that. Things that you're controlling here, or the input of our function, is X, Y, theta, positions in X, Y direction, theta, and then delta SR and delta SL, the distance that right and left will move, right? So if those are our input to the system, the output we have is actual motion in X, Y direction with some error. So the error is shown here with delta X, delta Y, delta theta. It could be also increment in the motion, right? If it's not desirable, it's called error. If it's desired, it's part of the plan. You know, you do something wrong, it's like, I planned for that. So your error becomes intentional, you know. Now, there is a very straightforward way of coming up with these. I just brought you the final equations, but basically what you're doing, you say that this wheel is going to go from here to here. If this was my theta, you have this distance is B. This is delta S. So if this was, let's say, right or left wheel. And then you have phi dot. So if you put all of that and write the equation, you're going to come to this for delta Y, delta X, and delta theta, and delta S equations, right? So I didn't write the whole process. You should be able to do that. If you needed help, I can send you a piece of lecture that has all of it. But we will use these four to calculate or estimate the position for our robot. Now, delta X, delta Y, delta theta is the path traveled in the last sampling interval, right? It could be the error, it shouldn't happen, or is part of the plan. We don't know. We're just going to call it the increment that happened, right? So you're from an initial position, X, Y, and theta, and you're moving to the next incremental position. Delta S and SR and delta SL, travel distance for right and left wheel, and B is the distance between two axle, which I have already, I think, mentioned it here, red. Yeah. So I called it 2B there, here, just B. So if this was, so B divided by 2, this is the center of your axle. No, axle is not like that. Axle is the other way. So let's say you're gonna have the other wheel here, right? This will be another B1/2. So the whole distance is B. Now, if we write those in like that, then we can get P prime or next position P XYZ plus just replacing those three numbers. So the equation for motion will be XYZ, XY theta plus those three delta values, the incremental values. Now, this equation becomes this. If we replace all of those delta S's with delta SR plus delta SR divided by 2, because in between, so the distance travel is divided by half. So this becomes our new equation of motion for position, right? We are trying to estimate the position. So what are we doing? What is your current position? How much time passed? With all the information we have, what's the next position, right? This increment is going to give us the next position, plus where we are currently. Now, where do you think the arrow will appear? So you are in an initial position, right? Time increment delta theta, you're going to the next position. Where do you expect the error to happen? So you expect the error to happen somewhere here, right? Somewhere here the error happens. Now, but you don't know how much error, what the error is dependent on. So we have to come up with a model that we can add to our equation of motion, right? Or here the pose estimation. This is just pose estimation. You need to add that so we can compensate, so we can model the error. Like if this is the position you expect, consider this much error in that, right? So to come up with the model for position estimate now, we are going to count for error of a motion error between a right and left wheel, which is which increase with time. Now this can depend on the velocity of our wheels, right? That was one of them that we said that it can happen. And the other one was if the axle or the steering wheel, the steering system is not adjusted. And then also the environment. These are the three things that we're going to count on. So this is just error propagation for everything. How does error propagate? So I had to talk about this because I wasn't sure if everybody knows this, but think about if you have a system, you have input and output, and you know the probability of distribution of the input, you know the probability of distribution of the output. How can you find a function that can relate these two together? So you have a system, you have some input, you have some output. You want to know how change in input would impact the changes on the output. How can we map these two? Because this is the map, right? You remember we've done this before. You have a system, you have an input, you have output. You want to know what's the function, that F function? What's the mapping that can relate the changes of the input to the changes of the output? Yes, Jacobian. So you're gonna see your friend back here. I don't know how much you love or hate it, but he's gonna show up. So the solution is to use Jacobian. So generally, we can use the first order Taylor expansion, and then we write Cy, the covariance matrix for the output, equal to Jacobian times the covariance matrix of the input times multiplied by the transpose of the Jacobian, so it's sandwich in there, right? Now, the covariance for the input uncertainty and output uncertainties is something that you'll have to either be given or you assume something, like depending on what kind of error you have in your input, you will come up with a covariance matrix for it, right? Depending on the probability or your modeling. There are ways that you can calculate them, but usually you can also use white noise or Gaussian. You can use Gaussian, and then it will, you'll be able to find after iteration, you will get the final solution, you will converge. So now the Jacobian will be that function f that we created that had the current position plus increment in position change with respect to different variables, right? How many variables we have in our function? 5. X, Y, K, F, delta SR, delta SL. So the position of, well, the distance that right wheel left move and the left, because if you have something in the structure of the wheel drawn, so you are getting the differentiation with respect to that as well, right? So considering those. Now, for the delta S, with respect to delta SR, the wheel, we can define this covariance matrix, covariance of delta SR and delta SL. So here, Ki and Kr are your error constant. You usually, when you're modeling for Kr, KL, you will usually calculate. So you will model, you will run a few tests to figure out what kind of error you have. Then you give a number, let's say 0.1, 0.001. So every time you move, instead of going 1 meter, you go 1,001, right? So you say this must be, then you turn right to see how much it impacts on turning right, how much on turning left, and say, okay, I'm going to say 0.01 on the right wheel error, 0.05 on the left wheel. So you run and see if what you get from simulation agrees with the real test. If not, then you adjust. So Kr and KL can be measured and adjusted, yes. Yeah. So the B, the distance is fixed, right? So where right and left wheel are, that length does not change. So you will measure, let's say it's supposed to be 2 meter, I don't know if 2 meter makes sense, but 1.98. Okay, you put 1.98. You already calibrated. Things that you can calibrate and you can measure, you will do it, right? So it will fix itself out right away when you measure that. So now delta SR and delta SL, so KR and KL basically are representing the non-deterministic because you don't know how to measure the floor impact. But you observe every time I go from this path, there's this much error in right wheel, there's this much error in left wheel. I'm going to assume this much error is because of like floor impact, right? And okay, so once we create this covariance, then we can apply and say that, okay, I have this covariance error. I'm going to find the covariance matrix P. So the P prime is your estimated position. So P prime is going to be divided in 2 parts. One, the motion component, right? Figure they come from the motion component, and one from the slippage of the component, the wheel slippage, the things that Kr and KL will come in. So we will use this equation to find sigma P prime, which is the covariance matrix for the estimated position. And then we will calculate. So I'm going to show you what you're trying to calculate here. So sigma P prime here will be this coming from the wheel, this coming from the motion. Now, if we develop the Jacobian, one for, because we need one this Jacobian and then the other Jacobian. The Jacobian, because of the motion, depends on three things, x, y, and theta, right? The Jacobian that comes from the wheel will also depend on the right and left wheels distance traveled. You don't have to come up with the Jacobian. These are the both Jacobian for you, so you can just use them. But if you didn't know how to find these, you will have to basically go and literally get the Jacobian of that big equation there for this two. So now that I have my Jacobian for right wheel and left wheel, then we can plot the position, because our position is the current position plus all of these errors that you will put here, right? So current position plus this estimation because of the motion, this estimation because of the slippage, and it will give you the actual motion path traveled. So if you plot that, you will get something like this. So if you draw the error propagation by, if you show it by ellipse, you can find how to do that using the source I gave you. What does it say? This says that if I was gonna go on a straight line, I might go like this. Then so the error propagated, right? What you could go on a straight line, that's one possibility. But there are possibilities that you could go maybe like that, then go to the other point. On the way, because of whatever is happening from the environment, you might go, but you never go beyond this. Worst case scenario that can happen is you'll end up there. That's valuable. Why? Why is this valuable? You can control it, right? So you know that worst case scenario control, like then you can control. So this is uncontrolled. This is just showing you the error propagation that you can have based on the distance. You can have this much error. So if you travel half a meter, this is what you will get. The error is smaller. It hasn't propagated. So you can control it sooner and then redraw the model and see what is your next. So this is always, if you're going on a straight line, the error propagation is always vertical, perpendicular to the path. Because you're supposed to go in straight, right? So the error propagation is on the straight path. But if you're going on a circular trajectory, your error propagation is not going to be perpendicular, but you still will have the bounds. So worst case that can happen is this. Now, this is with a specific value for KR. So this was plotted using those equations for a specific value of KR and KL. What was the value? I don't have it here. I think it was like 0.1. I think it was KR was 0.1 and KL was 0.001, something like that. So when you measure that, you measure and you just estimate those, then this will be the position estimate, right? So if this agrees with what you see, then when you're designing your PID controller, you're able to compensate properly, go back to a straight line, right? So this torque is called position estimate, but you're estimating the amount of error. And as you go further, if you didn't compensate it, it's gonna grow, but it's still bounded. You can estimate how much it's gonna be. All right. If you don't have any error and you run the car, everything you're supposed to go in a straight line goes on a straight line, then your KR and KS are 0. So the part for the, so this position is when you're estimating the position, this part becomes 0. Right? So all of your estimation is based on the motion itself. If you were supposed to go straight, If you are going, I don't know, 5 radian per second to the right, if your motor worked that way, then you definitely will go the distance that you want to travel. So this is what happens for the motion component, and that's what the wheel slippage happen, right? Let me see if I can pull up a code to show you how to code that, because we just talked about the error, but how do we, let's see if I can pull that up. How can we use those equations? All right, yes, here. Okay, I'm gonna share this. All right, so here you can write your odometry, and then I also have position update. So calculating ds, d theta, dx, dy, they're my component. Covariance of wheel slippage. So DSR and DSL are the values that output, right? Then you have to calculate the kinematic with respect to the position, and then kinematic because of the wheel of motion, and you will add those two together. So that's basically those equation that you saw, and then you get x is x plus x d, y is y d, theta is theta d, and you will see that you have to update your covariance matrix every single time if there is any change. And then if you calculate the odometry, you're just plotting basically. So here, CP, the initial covariance with position is 0 because we start at 0 position. But then in the post update, we are updating those values here, right? Every time we are moving, we are updating with that little theta. So you see that here is a 3x3 matrix. This one is a 3x2 matrix. And if you plot that, so this is going to just show, so in a going a straight line, that will be the error propagation for that, because I changed this here. So let's say if this was 0, and let's see what happens. That totally changed it. So you see that depend on the slippage. So obviously 0.01 and 0.1 is a lot of difference. So one wheel is done to, right? But if the difference was a little bit closer, so the two will kind of behave the same, but one is faster or one is maybe not adjusted or aligned enough with respect to the other one, then, so ignore that part because I draw on the first one. This will be your error propagation. So as you go forward, your error propagation is increasing since I'm on a turn. It's not vertical, perpendicular to the path, right? So worst case that can happen, I can either end up here or end up here on the next interval, right? So you're guessing what happens on your next interval. Then from here, you design your controller. Like, hey, I model my error. You can read it. You don't have to actually use this manually. You can feed your controller from this to tune your API code. Usually for car, like the mobile robot, you use all PID controller, all 3 of them. The main reason is you have error accumulation. So you have to have data report. For the manipulator that we use, you can get out of it with PD. But for these ones, because we have error, we have to use all 3 of them. Usually you see PID, but the values might be small. All right, time is good timing. All right, so that was it. I'm going to, no, I don't have to share anything. I will post the annotated version. I think I had a few things extra I wrote on the slide, but I didn't talk about it. I'll just add those. But in general, you can write the kinematic, you can write the dynamic, If you don't have any slippage, the dynamic is enough, right? You just have the covariance of the position estimate, which comes from, does your motor does what it's supposed to do. But if you know you have a slippage or you have bump on the road, then you have to count for that. You're basically remodel that, and then when you design your controller, you just compensate those, right? Cool. All right. Okay, everyone, have a great Thanksgiving. I'll see you on Monday.